Hello everybody, this lesson is going to be about a new gas law equation that we have not used yet. This one is going to be called the ideal gas law equation. Real quick, just a reminder that you want to use kelvins when you're doing these calculations. Remember that we need to make sure we never end up with a negative temperature because that can cause us to get answers for other variables that make no sense. We don't want to end up with a negative volume, for example. So we use the Kelvin scale, which is an absolute temperature scale. 0 Kelvin is as low as it gets. There's no molecular movement at that point, so we say 0 really means 0. So remember, it's called the absolute 0.0 Kelvin. So make sure you're using that for your calculations. This is the ideal gas law. PV equals nRT. Sometimes we just refer to it as PivNert, so it's kind of a silly way of saying it, but that means we can say it a little bit faster, a little bit easier. We just say, use PivNert. So if you ever hear me say that, I'm referring to the ideal gas law. Some of these variables are probably familiar to you. Some of them maybe are not. So let's walk through what each of these letters stands for. P is pressure. We've seen that already. V is volume. N is going to be the number of moles. R is something that's probably new to you. It's called the ideal gas constant. And T is temperature in kelvins. So what the heck is that R value? That's not something we've really seen before. So that's called the ideal gas constant. It's what we call a proportionality constant. It's basically going to fix everything for us. So when we use all sorts of different units, things don't always match up perfectly. So this proportionality constant is basically a correction value that is going to allow us to account for all the different units that we're dealing with. The number is going to change based on which set of units you're using. If you're using atmospheres, you'll use one number. If you're using millimeters of mercury, you'll use a different number. So you will have to pay attention to the units to make sure you're choosing the correct R value. Now, if we're ever using a real gas instead of an ideal gas, there would be a very specific constant that would apply to that specific gas as well. Not something we're going to worry about. We're not ever going to be dealing with real gases, right? We pretend that everything is ideal. Don't try to copy all this down. You can have it in a reference sheet. You can look it up. These are just some variety of the R values that you may end up using. Some of them are more common than others. On your reference sheet for the gas law chapter, I put the most commonly used ones that you see in this class: 8.314, 0.0821, 62.4. There's kind of 3 that we tend to use a lot. I highly suggest you memorize them. It's going to save you time. Okay, so my biggest suggestion is just memorize the 3 that we use a lot. Another option is you can memorize just one of them, and then every time you can convert your pressures to whatever that R value uses. So you could choose to always convert to torr and use 62.4. I feel like that slows you down because it's one more conversion you have to do. But if you ever forget what one of the R values is, you could always fall back on that as a backup option. So just kind of up to you what you find easier. I will say that a lot of the time the answer keys are going to be done using the atmosphere version. It's not that you have to do it this way, but if you want your answer key to match exactly, then that's the way I would do it. We should end up with the same answer though, right? We should have just a little bit of rounding difference if we use a different R value, but our answers should be within reason. On a quiz or a test, if it mattered which one you used for the sake of rounding, I would make sure to tell you what to do. or it would be multiple choice so that it would be pretty obvious what your options were. If you'd keep track of your units, because of these crazy units on R value, you'll be able to make sure that everything cancels out correctly. The way we say these units would be liter atmospheres per Kelvin mole, or it could be like liters, millimeters of mercury per Kelvin mole, or liter torrs per Kelvin mole. That's kind of how you say that. The little dots are multiplication symbols. It's traditional to just put a dot because otherwise your work starts getting really, really messy with all these little multiplying symbols. So it's just kind of typical that when we're using these complex units, these derived units, you just put a little dot instead of a multiplication symbol. For the most part, using the ideal gas law is very similar to the others. You list your variables, you plug them in, you do some algebra, move things around, isolate your variable, get the one that's missing. So I'm not really going to go through and do practice problems on that. Our math skills are strong enough. You plug in and you find what's missing. Okay. One thing that is a little bit strange with the ideal gas law is that sometimes we rearrange it in creative ways to solve for things you might not think of at first. So for example, if you use the ideal gas law, you can calculate density and molar mass of an unknown gas. Big suggestion, just memorize the two final equations. Memorize the equation for density, memorize the equation for molar mass. One of the things I see so often at this chapter is that people forget to study these two. And I promise it'll be on a quiz. I promise it will be on a test, right? We don't have a lot of practice problems for them because they're relatively straightforward. They don't take a lot of repetition to get good at, but they're still important. Please don't forget to study these concepts. Now, with that said, if you are thinking of taking AP Chem in the future, I'm going to give you the strong suggestion that you practice rearranging to solve for the equations yourself, and I'll show you how to do that in a minute. The reason I'm suggesting that is one of the things that AP Chem problems love to do is they love to give you data that looks like you don't quite have enough numbers, and they want you to rearrange your equations in really complicated and unique ways to try to find the thing that you're looking for. And so a huge part of the AP Chem problems are substituting and rearranging and finding unique ways to do that. So this is a perfect example. So I'm going to show you how to rearrange to find molar mass. I'll show you how to rearrange to find density and maybe give a little bit of a practice that'll get you a good head start for AP Chem. Okay. So, a couple abbreviations. Most of these you already went through, but there's a couple at the end I want to make sure you are aware of. P is pressure, V is volume, number of moles, ideal gas constant, temperature. Those we just saw a few minutes ago. But the two that you may not be used to seeing as an abbreviation, as a variable, would be molar mass as a capital M. And then the lowercase m is the sample mass. Those are going to be important. Now, the idea here is that we need to be using the ideal gas law, which has moles in it. So what I'm going to do is I'm going to think to myself and realize, wait a minute, if I'm calculating molar mass, I'm going to use grams per mole. So if I want to find moles, that would be the mass over molar mass. So what you can do is you can substitute in, instead of putting N in your equation, you're going to stick in mass divided by molar mass. Remember, we don't know what molar mass is yet. That's what we're trying to solve for. I know the pressure of the gas. I know the volume of the gas. I know how many grams of the gas I have. I know the ideal gas constant, and I know the temperature of the gas. So what I'm trying to find is the molar mass of this unknown gas. Now I'm just going to do a little bit of algebra to try to get that mass, the molar mass, the capital M up on the top. And I'm going to isolate it. And we end up with molar mass is going to be the sample times the R value times temperature divided by pressure and volume. So you can, in theory, start at ideal gas law and work your way towards knowing this equation. Or just memorize it, right? That'll be faster. All right, the density one's a little bit more complicated. Let's review what density even means because sometimes we forget, we don't use it very often. Density is going to be how much stuff do you have crammed into how much space. So density is mass over volume. Remember, we can rearrange with molar mass to say that mass is moles times molar mass. Or I can say that moles is mass divided by molar mass. Those are all just rearrangements of the idea that we have grams per mole, right? So we can rearrange and get different versions of those variables. So we are going to start once again with this concept that the number of moles is the mass that you have divided by your molar mass. We have our ideal gas law. You substitute in. Now, let's think for a minute. Density is mass over volume. I have a variable for mass and for volume, but they're not together. They need to be divided like this in order for it to be density. So what I'm going to do is I'm going to rearrange this to try to make it look like our density equation. So I end up with M over V is capital MP over RT. And if you look, right, that's the same as saying density. Okay, density is molar mass times the pressure divided by the R value times the temperature. Okay? So that's one of those handy equations to know or be able to rearrange for. Now I'm going to show you one more about molar mass. This one's a little bit silly. It has a funny way of remembering it. It's a pretty silly way, but it's pretty classic. So here's another way to use density to help you find your molar mass. So we have the equation molar mass is MRT over PV. And if you look, that's the same as density, the M and V, right? So instead of putting them separate, I'm going to just replace them with the D itself, right, that I'm getting from up here. So this is a classic way to remember it in this format because there's a silly little way to know what it is. We say molar mass kitty always puts dirt over its pee. So obviously a weird way to remember it, but it's strange enough that most people tend to remember it when you tell them the little silly joke here. This is the picture of the cat that I have seen on so many different teachers' PowerPoints. It's like the classic picture to use when telling people about this version of the molar mass calculation. So hopefully that's silly enough that it sticks in your head. Molar mass kitty. Okay. And then one last thing I just want to talk about is we call the ideal gas law ideal, but that doesn't mean that it's perfect. Okay, it's only going to work for ideal gases. We have to remember that the ideal gases are imaginary. They're not real. They pretend that there's no volume and no attractive or repulsive forces, which is crazy because that's not real, right? No, all gases take up volume, right? The atoms themselves have volume. And they all have some level of attractive or repulsive forces. So we have to use these correction values in order to be able to take the ideal gas law equation and adapt it to work for a real gas. So you can see here, instead of just pressure, you have to have this crazy calculation in order to account for the molecular attraction or repulsion that might be happening, because that'll change the pressure, right? And here in the volume part of the correction factor, we have to take into account that the molecules themselves take up a little bit of space. And then remember, you may have a very specific R value as well. And so it just gets way more complicated if you're ever going to try to do this with a real gas, which, lucky for us, we're not going to do. We're only going to do this for ideal gases. You just need the good old-fashioned PIV-NERT version, okay? I like showing this to you because I think when you see the correction values, it helps you remember what the difference is between a real gas and an ideal gas, because that's the kind of question we're always going to ask you is, what makes a gas ideal, or which would be more ideal, right? The one that's less polar because you have less attraction, or the one that's smaller because you have less volume. So I don't at all expect you to know these correction factors, but I think for some people, it just helps stick in your brain the difference between real and ideal. All right, everybody, that's it for this video. I hope that was helpful. Bye.